So yeah, today we're going to talk about, well, title is Sound of Your Secrets. We're going to talk about acoustic side channel attacks, and we're actually going to discuss building a machine learning model to detect keyboard sounds and then being able to determine what keys you're pressing. So my name is David Von Thenen. I'm an AI ML engineer. I love doing this stuff. It's kind of fascinating, all the technology and the things you can do with it. I kind of do everything from like AI to on like edge devices, vision models, even building machine learning models to detect like Parkinson's disease. This topic is also going to be quite interesting, hopefully entertaining, and yeah, let's jump into it. So the agenda today, we're going to talk about the moral duality of AI and ML. And the reason why I'm going to start there is because this is a very touchy subject. I'm like actually talking about something that you could build to do something potentially illegal, right? And then we're going to discuss building said thing. And we're going to discuss the data pipeline, the architecture, how to build it, the different problems we're going to solve. And we're going to do this driven by live demos. So there's actually 5 that I'm going to do here. We're going to talk about then applying this to the real world, like real world attack vectors. And then we're going to talk about how to like protect yourself against from this stuff. It would be really a shame to just say, hey, you're screwed. You can't do anything about it. But we're going to talk about how to protect yourself. So let's go ahead and talk about the moral duality of AI. Oops. You know, there, you hear in the news, you have the extreme good, like it can save the planet, and then the extreme bad. And so here's this tweet by Elon Musk, right? He talks about like AI comes, it can help us build things and do things so cheap, and it's going to be so cheap that there's going to be universal high income. Well, you know, while I love to believe this is true, it's probably not going to be the case, right? And just if you think about it, like not everyone can drive a Ferrari, right? There's got to be limits because of resources. And then here's the other side of things, right? Here's a article clipping saying from MIT saying, hey, AI can already automate like 12% of the workforce in the United States. And the number of programmers is the lowest and it's about the same level as in the 1980s. And the article distinguishes the difference between software engineers and computer programmers. So like software engineers, you build and you plan, whereas programmers, you just kind of like build out without kind of like doing the planning steps. But you can see the flip side of it is it has the potential for high impact. So if you think about all the tech, like from just a technological standpoint, this is an example of like the extreme good that you could do from it, right? This is an NIH article, so a National Institute of Health article saying, hey, we're applying AI to like cure disease. And if you look at the extreme case of this, maybe we'll be in this weird future where AI can help us like solve all diseases, right? So we have none. So I'd love to believe that. But the flip side to it, if you're not aware of what's happening, I don't know if it's happening here, but I can tell you it's definitely happening in the United States. They're using machine learning algorithms to maximally extract your money. And I don't know if you have digital, when you go to a grocery store, I don't know if you have seen digital tags. Those digital tags, and depending on the company, will update the price based on the day and the time of day. And high traffic times will have higher prices, and lower traffic times will have lower prices. And that's not even to say like using an app, right? By the way, if you don't realize using an app, the price is different than what it is in store. So just be aware. So this is the extreme negative of using machine learning. And why I'm bringing all of this stuff up is because we're going to do something that's in this weird moral gray area. And I'm actually built this. I didn't invent this, right? It's actually based on this research paper, and they've actually built this out. So this session really starts with this paper. It's an archive paper that says a practical deep learning based on acoustic side channel attack on keyboards. And I basically took what they had and I implemented it, and I made a ton of improvements on top of it. And so we're going to go ahead and discuss how to do this today. Oops. So building an acoustic keystroke logger. Let's go ahead and talk about it. So first we need to like kind of understand how to go about doing this. And believe it or not, like there's been like audio classification, building machine learning models that detect sound and then can classify that sound as things, right? And the way you do this is you take a sound, a wave file, MP3 file. Typically, what's used is a wave file, so linear 16 format. It's pretty easy. It's universal. It's standard. And you take that wave file and you convert it to an image. And so that's that image in the upper right-hand corner there. You can actually see this is a wave representation of a single sound. And you can see on the bottom, you have the time axis. And then on the y-axis, you can actually see the frequency. And then the little picture, right, where you can see the intensity of the frequency. So like that's what all those colors represent. So when you convert a wave file into a picture, this is what it looks like. And you can actually then see, if we do this for many, many different sounds, some sounds that are the same, you can actually take a look at the bottom picture here where each cell is one unique sound. Each cell is a different sound, right? And you can see that some of the sounds, just by looking at it, you can see that some of the sounds must be similar because they look pretty close to each other. And you can see other ones that are different sounds, so they represent different sounds. And so if you actually take a look at this, this has been happening in the world for a while. So if you start simple, like you can build a classifier to detect a cat meowing and a dog barking. And you can actually, and there's all the links work, so you can click it when you get home. They've been basically like other machine learning models that will detect gunshot sounds in urban settings, right? To alert the police that stuff is happening. But they need to distinguish those gunshots from a car backfiring, right? You don't want to alert the police because a car, backfired, right? So this has been happening for quite some time, but it is doable and it is possible. And here's another example. I actually gave this session last year. So I built out a sarcasm detection multimodal model. So using sound and facial characteristics to actually detect sarcasm in different TV shows. This was recorded. So I actually embedded the video here if you want to take a look later. But you can actually gunshot sounds, dogs and cats, or detect sarcasm in TV shows. Definitely go ahead. It's kind of a cool presentation. We're not going to obviously watch that today. So let's start like decomposing the problem. So like any ML or AI problem, it always starts with the data set. At the top, we're going to actually have two data sets we're going to talk about here today. The first is keystroke noiseless final. So this is actually a data set that was collected for a hackathon in Singapore, I guess, in 2024. And it's a data set that's a single keyboard, so like one keyboard. And they collected multiple sounds for like the letter A, the letter B, the letter C, and so on. And so this is literally the first part of the session here is we're going to duplicate that and kind of like understand what happened as a result of that. The second one is the multi-keyboard acoustic data set. So this is using multiple keyboards, so like Lenovo, HP, and capturing all of the sounds for every keystroke or every click of a keyboard, and then being able to classify which keyboard it is and also what sound, right? Like the letter A, if they hit the letter A, right? There's no need to like copy any of this stuff down. The slides are in my GitHub, so you'll have all the links and stuff to get the data set and get all the code and everything. So now that we know that we can take a sound and convert it into a picture representation for said sound using these spectrographic images, we basically just need to like extract them, extract the wave file to pictures, put the pictures into the representative folders. So like for A, we'll put them in folder A, for B, and so on. And we'll do this for 38 different keys. So A through Z, 0 through 9, space, and enter, right? And because we're classifying these sounds, which is basically frequencies over time, we're going to use a 3-channel classifier. And the reason why it's 3 channels because this is a color picture, and we're basically using the pixels and the color at every pixel in order to like be able to classify these images as a particular sound. And there's a bunch of other things you're going to do, is like normalize, because every key press doesn't start at the start of the the picture. So things get shifted around, and we use our machine learning model to like help normalize and shift things around so that it can understand when there's a small delay from pressing a key. So I'm going to go and skip over this slide in the interest of time, but you can look at the architecture here. It's a CodesNet style architecture. It's a neural network type architecture, all this fun stuff that gets associated with it. But I'm going to skip over it because I don't think this is like the most interesting part, considering this has already been done before. But if you want to look more into it, I have the links that are there, so you can learn more about how this thing was built, the architecture, and that kind of stuff. So let's go to our first problem here. So we're going to use that data set for a single keyboard. And we're going to take the data that's there and break it up into 3 categories. The training data, which is, I would say, roughly 70 to 80% of the data. We're going to use that to train our machine learning model. And we're going to use the same data, right, the same keyboard sounds, and we're going to earmark 10 to 15% to validate the model, right? This is the idea between validation and training data, is you use the validation data to get the model to reproduce and be able to classify every sound. And the closer and closer you get those 2 things to converge, you basically get a classification of 100% if you can do that, right? And then you use the test data to basically verify the model's built, what kind of results you're going to get, how accurate it is to like a certain percentage. So this is kind of like what we're going to do. And we're just going to go ahead and show you and just do it right here. So can everyone see that? Cool. Okay. So this all starts with the sounds, right? The wave files. So we're going to go ahead and take a look at the data here. I severely reduced the scope of the data because we're all going to do this live. But you can see that we have test, training, validation data. And then if we go ahead and look at the training data, just the letter A, you can see we have all these wave files here for the, what to classify the letter A, right? Based on sound, based using wave files. And you can see that we don't have an image folder. So what we're going to do is we're going to go ahead and we're going to convert those wave files into images. And so now if we go ahead and we look at the images folder, we'll just go to the training data, the letter A. You can see we have images, PNG files for the letter A, and each one of those files represents an instance of a sound, right? The letter A. And if we go ahead and we open this up and take a look at this, this is 05, so the 5th instance for the letter A. So that's what it looks like in a pictorial form, right? This is what A sounds like. Now, let's go ahead and back out of this. So now we have a mechanism to actually convert the sounds to pictures. Now we need to actually train the machine learning model to recognize said sound, right? And so if we go ahead and we put the data, we have converted all of our images. You can actually see, for example, data, I think it's this one right here. Training, test, validation, training. So these are all the different letters that we want to classify. Letters, numbers, space, enter. And if I just pick a letter at random, B, you can see those are the PNG files that represent sounds, or wave files for the classifier that we want to build, right? Now, if you want to train this model yourself, you can go Python 1_train, and you hit enter. It will take the training data. It will build the machine learning model using the images there. If you use an H200, it will take approximately 14 hours, just FYI. So it takes a lot of time to actually build this. Now, if you don't want to do that, I have included the final model to actually, so you can just download the model that I had created, and you can run inference locally on your laptop. It's a tensor safe format. It'll run on any laptop. And we're actually going to do that. And if we take a look at the this cool little pointer thing. So s-09.png, so that represents the sound S. We're going to take that image and run it through our machine learning model, which we've already built, which is the top one right here. And we're going to see what kind of result we get by passing that sound into our model. And to run inference, we're going to go ahead and go to_inference. And you can see that classification for that sound is 100% accuracy. So if we have a single keyboard, like a known keyboard, and we take all the sounds and we build a machine learning model to like classify the sounds, we can do it with near 100% accuracy. So pretty interesting, pretty amazing, pretty scary, right? So you can actually do that, and you can do it to a disturbing degree of accuracy. Let's go ahead, and now let's move on to multiple keyboards. So we have, now we're using that second data set. So we have multiple keyboards, sounds for multiple keyboards for multiple key presses, and we're using a Lenovo keyboard, an HP, Apple, MSI. Now the two ones on the end are scary. Take one of the keyboards, record the sound over Zoom, and do the same thing for Messenger. So, you know, if you are ever typing with your mic unmuted, be aware, right? You can actually do that, and it actually does work, which we're going to show in a second. So if we take multiple keyboard sounds and multiple key presses, we're going to do the same thing. We need to create training data, which is 80%, create validation data, which is 10%, and create test data to actually find out what the accuracy of our model is at the end. And so we split up everything so that we have representation in every training validation test. So instead of just sitting up here and talking about it, let's go ahead and take a look at it. So go into our 3 training multi-keyboard dependent data set. And again, let me just clear this out. If you want to train this model from scratch using the data set, so if we actually look at the data set, right, divided into test, train, validation at the bottom there. And if we go look at the training, you can see all the keys just like before, except the difference is I'll just pick a key at random, right? So the letter N for our training data and the validation and the test data is the same, except they're in smaller quantities. So you can see the HP, there's like 1, 3, 4, 5. So those are the different instances of a key press for an HP keyboard, for Lenovo, for a Mac, for keyboard over Zoom, and so on. And so if we actually want to train this model using that data, same thing. You can do this at home, use an H200, 14-ish hours later, you'll have a model. But we obviously don't have the time to do that. And if you don't want to burn the money to do that, I totally understand. I've provided the final model so that you can run on your laptop at home as well. And so we're just going to run inference, and we're going to take one key, which is that H Lenovo 5. I've just picked one randomly. And we're going to take that and we're going to pass that through our machine learning model to see what kind of accuracy we can get using that picture. So you can see right here, Lenovo, it can actually detect that it is the letter H, but you notice that it's at roughly 48% confidence that it knows that it's the letter H. And then the letter J is at roughly 16% confidence, and then the letter K is 4% and so on. So you can see that it's not nearly as accurate, but it's still able to actually, like using and this is like a top K of 5, it's still able to accurately say with 48% confidence, I know this is the letter H. And why this is important, keep this in mind, because we're going to use this little portion here as a part of the improvement that I made to like what they had originally tried to do. So, yeah, pretty crazy. It had occurred to me, right, that if we wanted to like try to improve that, we should probably consider some out of the box thinking. And in order to determine, to get like a representative sample of like me typing, what we're going to do in this next one is we're going to go ahead and we're going to, I have a bunch of sounds in this examples folder. I just picked, obviously I need to be consistent, although I could switch it up, but just for consistency's sake, it's all the Lenovo sounds. I picked random letters, which you can see right here, like the letter A, C, D, E, and I'm going to take those sounds and I'm going to string them together to compose a message, which would simulate me typing something to, and use, if we recorded that entire message, passed it, chopped it up, passed it into the machine learning model to classify each independent sound, we're going to spell out a message. And so just for argument's sake, let's go ahead and take a look at it right here. So this is the message that we're going to try to spell. And you can kind of already see the message is hello Paris, right? So the letter H-E-L-L-O space Paris, right? So let's go ahead and take those sounds and pass them through, pass them through our model and see what we can get. And again, this is the multi-keyboard model that can classify multiple keyboards and sounds, right? So, right, again, we're trying to spell out hello Paris, but you can see that the first part's actually not that bad, right? H-E-L-L-O, which is the top letter that it thinks it is, and you can see the corresponding confidence scores. And then these are the next ones. But in this particular case, we actually were able to classify hello and be all cool. That's hello. And then space, right? And there's a reason why the space is actually quite unique, which we'll talk about in a second. But space, so as a new word, right? Then we start to run into some problems. If we just only looked at top K equals 1, so used only the one letter, O-S-R-I-D, which is not a word. But when we set top K equals to 2, we can see that we have the other letters we need. So P-A, right? The first one, P-A-R-I-S, right? So this is the small improvement that I made to actually, they were only looking at top K equals 1, but if you go top K equals 2 or 3, the letters are there. It's just that they're like slightly less in confidence than the other ones, right? So we need to figure out a way of actually retrieving that word from the garbled letters here. And what we can actually do is, again, the improvement is take those letters and basically try every combination, pass them through a spell checker, and find out which one gives us a word and say, that's a word. And that's what we're going to do in this next one. And hopefully the internet will cooperate because I'm going to literally do the spell checking live. Now, it should be noted, right, we have 5 letters, 2 words, 11 keystrokes. Now, we can't do every possible combination. Otherwise, it would be, 2 to the 11th power, which will take us that many attempts in order to figure out like what word it is. But there's one thing that's very unique about this particular situation, and it's the space key. So that space key is very unique. And the reason why it's very unique is because it's a different size from all the other keys on the keyboard. And it's going to have a vastly different audio signature because of that. And so we're going to use the space key to delimit words, so we don't need to test all the possible combinations. So the first one, we just need to run the first 5, run the possible combinations. So now it's 2 to the 5th, space bar, 2 to the 5th. And those are, we only need to now run 32 combinations for the first word and 32 combinations instead of 2 to the 11th power. And so that's the other improvement. And we're going to go ahead and try that right now. And when we run this through our spell checker, we're going to output, when we hit a word, we're going to output that word to the console. And we're going to just print it. And we're also going to print it to a file so that we can, in a very cool way, see our final message here. So if we go ahead and take the keystrokes, pass it through a spell checker, So you can see that the inference, just like before, this is unaltered. Run it through a machine learning model, determine what the keys that it thinks are for top k equals 2. And you can already see we're working on the first word right here. And it's already found through our passing it through our spell checker, the 32 different combinations, pass it through the spell checker, hello has been identified as a word. And what it's also going to do is, just like any machine learning problem, it's all probability based. So why not just dump all the other possible words anyways? And you'll hopefully see that in a second, depending on if the internet will cooperate with us or not. Keep going. And so then we're going to use, so there you go. So you can see the top one, most probable hello, it is a word. Great. So we've identified the first word. You can, using the space bar as a delimiter. Now we're working on the second word, 32 different possibilities. And we can make improvements on this. Right now I'm dumping, so based on these possible combinations, I'm dumping words, right? That running it through a spell checker based on this word, what possible word could it be? And this one is help. Now, if we wanted to make an improvement on top of this, we could junk that word. And why? Because we know the word is 5 characters in length and this is only 4, right? And so we can make more improvements on top of this. And so this one identified 2 words. I don't even know if that is a word, but whatever, we're going to record both of them. And if we go ahead and we cat out our file, we have our message, hello Paris. So using multiple keyboard sounds, able to type away, and then using a machine learning model to be able to classify and understand what keys you're typing based purely on sound alone. And yeah, it's quite frightening. But let's not stop there. If you were going to try to automate this, and you know every once in a while this thing's not going to work 100% perfectly. And so occasionally you're going to get one word that's going to be like, it couldn't figure out the spell check. This thing looks like garbage. You put in your best guess and it's like it doesn't sound correct, right? So what had occurred to me was you could build a machine learning model, an AI model, to attempt to guess what word that should be. And so I created a masked learning model that will basically, who here has heard about the game Mad Libs? I know it's like an old, yeah, it's a very super old game, but it's like a word game. And basically the idea is you have a sentence and they have a bunch of gaps in them. And where the gaps are, you ask your friend, give me an adjective or give me a noun. And your friend would then give you an adjective or a noun. And the idea of the game was that you give an adjective or a noun that was completely random, that would sound funny, and then your friend reads the sentence back to you, and you all have a laugh because it sounds ridiculous. So it's the same idea, except for where that blank is, we're actually going to guess the most probable word that should fit in that spot. And so I built a machine learning model to do this. And so what we're going to do is we're going to pass sentences into this model, and we're going to leave a gap for this model to guess what word should be there. And so if we go ahead, and we're going to just give you a couple example sentences. So the first sentence we're going to throw in there is the capital of France is blank. And based on that blank, the machine learning model decided that the most probable word is Paris, which is right. And then we have just another example is distilled models are the blank of large models. And we have the top 5, but the top k equals 1 or the most probable one is smallest, which is correct. So if you were trying to automate this solution and you're trying to build a thing that doesn't require any human intervention, you have trained a machine learning model based on multiple keyboards or a single keyboard to try to figure out, based on the click of a keyboard, what letter you're clicking. then pass it through a secondary thing where we do spell check to make sure that the words that we're identifying, the letters, right? The combination of letters are a word. We're going to pass it through a spell check to make sure that the word is correct. And for those words that we screwed up, we are going to omit the word, pass it through this machine learning model, then to tell us what word do you think that it is. And it'll reply back saying, I believe this word is this word. And maybe you can automate the entire thing, the entire pipeline to be able to tell you what someone is typing based purely on sound. So pretty crazy, right? So let's do a recap. So a single keyboard. So if we're taking a single keyboard, we're trying to learn and identify and classify the sounds based on a single keyboard. The accuracy is 100%. That in itself is frightening for the next section, which I'm going to talk about in a second. Now, multiple keyboards. I took the test data. I said, give me what you think that the most, what your top K equals 1. I want you to take one shot at it. Tell me what the letter is. If you get it right, it's wrong. Right. If you get it wrong, it's wrong. 46% of the time, it could tell that it could give me a result that was the most, what it thought was the most confident score, and 46% of the time it was correct. Now, typical machine learning problems, that's not that great. You usually want something 80% or higher, but that's actually really good. And the reason why it's really good is because we only are looking at 38 keys. And if you were to randomly guess what word or number, or what letter or number it is, just that probability of you getting it right is 3%, right? 1 divided by 38. And having that number be 46% versus 3% is actually pretty good. And the reason why it's pretty good is because if we start to do top K equals 5 and consider the next problem, the next confident and then the next one, we can start to string this thing together to actually figure out what word we're typing, even though statistically 46% is not great. So by applying like top K greater than 1, using different permutations by looking at the first most probable, the second most probable, and then using AI to fill in the blanks, this actually becomes a real world mechanism to figure out what someone's typing. So one thing I didn't test, although I did actually test in the sarcasm one, which is why that one's kind of very fascinating, is the model is trained so that it must know about the keyboard. So you can't just like introduce a new random keyboard and figure out based on the sounds if it can determine what those clicks are, because those sounds are very unique and it needs to learn what those sounds sound like for that given keyboard, right? And when you do independent, so like an independent data set, so you train a machine learning model and then introduce a new keyboard to test, this one starts to go downhill fast. And I know for this particular problem, I'm guessing it will probably be close to, if not the 3% probability distribution, in which case it's not going to be favorable to you. So I didn't test that because I knew it probably wouldn't be great. But I'll leave you with this. What about manufacturing similarity? Suppose if we take 2 keyboards in the same manufacturing lot and we record the sounds on one, but attempt to use the same exact keyboard made in the same lot to try to determine what that sound is. I actually think that would work. I did not test it. And the reason why I think it would work is because of this little column right here. Right here. This is the frequency at which you hit letters when you type normally. And basically kind of like, you use the letter E the most, right? 12% of the time. So my contention is the wear and tear on your keyboards, just based on normal typing, is what will contribute probably very heavily to the sound. And if you're using 2 keyboards in the same lot, I'm willing to bet that there are probably manufacturing differences so that wear and tear is the same. And so you would actually be able to use the machine learning model on a second keyboard. So just if anyone wants to try that. Part of the problem is I didn't have a data set to do this. So How could we improve on this even further? So we captured both data sets we're capturing the sounds independent. And when you type normally, there's like a certain rhythm to typing, right? You, based on the way you position your hands, you move one to the other. I think it could have a small effect on what the next sound is. So if you were actually to try to do this, you maybe want to consider what key was pressed before it, and then train, basically have a branch to say, if I think it was the letter A, then the next key might be the letter U for like authentic, right? Because A follows U. Maybe that small little difference could make a difference in the way it sounds. But also my contention would be if you were just to collect enough sounds that you could probably statistically remove that, so you wouldn't need it. But then you start to run into things like how different people press keys. Some are more heavier set, like hit the key, like slam it down, versus lighter, typing. I like using home row, like the positions, like, home row, like when you're typing like that. I don't do that. I hover and I peck at the keyboard because I just memorize where the keys are. And I think that might actually have some effect on that too. And obviously, if there's noise in the background. So let's talk about real world attack vectors. So this isn't a new thing, like what I'm describing. Back in the 80s, if you know about this kid's cereal, Captain Crunch, there was this whistle, and if you blew on the whistle at a payphone, it would actually give you free phone calls. This was in the 80s, 90s, because the dial tones, the sounds, was how it determined like initialization, what keys you were pressing, and that kind of a thing. But I was thinking about what would be a good real world problem where we can take a single keyboard and identify an attack vector for one single keyboard that everyone uses. And the first thought I had was this: a keyboard that everyone uses, that you could probably record the sounds on, go up to it, record, hit one like 3 or 4 times, record it, and then come back the next day, hit 2, then 3, and then just kind of go there. And those credit card skimmers, right? You put over the thing where you slip your card in. How about embedding a microphone into it? And when you put your ATM card into the credit card skimmer, that triggers the microphone to start listening. And now you can pair the pin to that card, right? Pretty frightening. Don't do this at home, please. So like, what about multiple keyboards, right? If you have, this one's a little bit more, far-fetched or like wacky, but if you have your keyboards lying around, there isn't any reason why someone couldn't potentially record sounds like for the keyboards at home. And, hackers are going to look for every advantage, right? Maybe they can't put a keystroke logger on your computer, but maybe they can put something on there to listen to what you're typing. And if they can grab the sentences you're typing in a Word document and then make the correlation between the two, maybe that's one way they can figure out like the password you're typing in, right? So how do you protect yourself against all this stuff? So 2-factor authentication, like this is obvious. If you aren't doing it, please do it. So use a YubiKey or whatever it is. Don't use SMS, because there are actually ways of like receiving text messages, believe it or not. Use strong passwords, and ideally make sure you don't know the password. So you can't socially engineer what password it is based on your kids' birthdays or what your favorite football team is or whatever, right? So you can reduce the scope of the attack, right? Use a different password for every platform. If you have one password for like all your bank accounts, one compromised password, because passwords get, platforms get hacked all the time. One compromised passwords could snowball into a bunch of other ones, right? Access to a bunch of other ones. Change your password frequently. I know everyone hates to do the 90-day password thing from your company, but there's a reason why they do that. And be intentionally difficult. So if you screw up typing in your password, I don't intentionally do this, but if you screw up typing your password, Now the sounds could potentially interfere because now you're having to hit the backspace button and you retype part of it. And there's a reason why in like spy movies, you turn on the radio as you're trying to talk about your clandestine plans, right? There's a reason why you do all that, right? It's to be intentionally difficult for you to record the sounds. So I'm talking about this stuff because this was like an article, right? Apple acquires this cool startup. They have a cool patent in the US for interpreting microfacial movements. So the first thing I thought about when I saw this was actually this. If you can detect facial movements, microfacial movements, you should be able to determine what someone's saying without any sound at all. And with Apple wanting to put cameras in their earbuds now, which I've heard is going to come out maybe next year or something, it starts to get really scary, right? So resources, everything, slides, code, the models, so you can download them and try this yourself. They're on my GitHub right there. And if you're interested, there's the data set, the original research paper. I actually spoke at Devoxx France last year. There's actually a really cool, if you're talking about wanting to screw around with AI to do things that they're not supposed to do, it was recorded. So you click that, you can watch the video that I presented last year, which is basically trying to disrupt AI to do things that it's not supposed to do. And there's also the link for that sarcasm talk too, so you can watch that video. But thank you.